Good morning, good afternoon, and good evening to all the viewers there. Any part of the world, you must be watching this. So that's why I'm saying good morning, good afternoon, and good evening. This is Rajiv Kulkarni, your host for Global Electronics Friday Talk Show. Every Friday, we bring in some special guests talking about different topics on electronics manufacturing. Yes, we are focusing on electronics manufacturing and the challenges, the activities, and what are the impacts which are happening on a day-to-day basis on the trending, that we are talking these days, the globally, how the electronics manufacturing is moving and what pace and in which direction it is moving. So today we have a special guest, but before that, I would like to thank all of you because you take this time of your valuable time to listen to our guest and try to learn something out of it. And our goal is to definitely deliver the best knowledge that we could from their wealth of knowledge. So let's start today's topic, which is materials reliability on electronics. Yes, materials reliability in electronics is crucial to ensure the performance, safety, and longevity of electronic devices. And having said that, if we prioritize the materials reliability in electronics, manufacturers can create more robust and efficient and safe devices that meet the demands of various applications. So this is a topic today. And to talk with us, we have a special guest, and she is definitely from the United States. But just to give a little background about her, she is a program manager at Keysight Technologies, and she manages materials reliability investigation plus Keysight's engagements with electronics manufacturing and reliability consortia. She has experience with the printed circuit design, assembly, and reliability, and also failure analysis, contract manufacturer relationship management. That is very, very, very important. And also she is engaged in sustainable manufacturing and leading global teams. So ladies and gentlemen, let's welcome Ms. Julie Silk from Keysight Technologies. Julie, good morning, and thank you very much for joining today us on the Global Electronics platform to share your wealth of knowledge on the reliability of materials in electronics, how important it is, what are the benefits, and what are the factors needs to be considered, and so on and so forth, and how Keysight Technologies use their resources, use their technology front in terms of handling the reliability management. Welcome to the show, ma'am. How are you this morning?
I am doing good. Thank you so much for inviting me. It's quite my pleasure to be here. So, as a background for Keysight, a lot of you may know this, but our origins were in Hewlett Packard. We were the test and measurement portion of that, which is actually their origin was test and measurement equipment. And then we became Agilent, and then after that we split again and we became Keysight Technologies. So we have a very long history of creating reliable products, and we expect to continue that into the future. So I have a little video I'd like to play. So let
Yes,
me share, and then just for a little blurb about Keysight.
absolutely, absolutely.
Um,
Oh, no sound.
Okay, did that work out?
Yes, it is.
Okay, good.
Excellent,
Good. Okay.
except the sound, because normally when it comes to the very serious discussion, the sound, when there is no sound, it's it's better because people can focus
Okay.
more on the
Well,
video.
there was only music, so that's
Yeah,
fine.
yeah.
So
Yeah. Okay.
anyway, so yeah, we do test and measurement solutions, and our customers expect our products to last for a very long time. They get calibrated every other year and then people have them they still have them with Hewlett-Packard markings on them. They still have them with Agilent markings on them. And our customers have high expectations for products that last a long time. So I manage our design for reliability programs and our reliability investigations. And so I'd like to cover a few things, and then there'll be plenty of time for questions.
Absolutely.
Okay, so this is a definition of reliability that I like, where reliability is the ability to function as expected under the expected operating conditions for an expected time period without exceeding expected failure levels. So various people have said this. And it's a really good definition. So your expectation for a child's toy is really different than it is for a piece of equipment that you spent $100,000 on, right? So we our products say can be repaired easily, and there can be a certain failure rate because we're not mission critical. Like say my presentation has nothing to do with the um, aerospace and defense industry where their expectations for reliability are extreme. You don't want a satellite to
Yeah.
break, you can't fix it. So, anyways, I'm going to cover a few things. Design for reliability. It's the process of preventing or eliminate design-in failures. So you could design in stresses, and a lot of those cannot be resolved with a process change. They cannot be resolved with rework. That there's something fundamental in design that is causing a failure. So if you have reliable products, it is worth it for your financial goals of the company, and your customers are a lot happier. So the costs for rework or replacement or redesigning is very expensive. So you really want to design that in from the very beginning.
Hmm.
So principles, you have to start with manufacturability, high quality components and suppliers and processes. If you have poor quality, you have early failure. This over here is an example um, of a calf failure. So conductive anodic filament has grown because basically it was a poor material, the drilling was rough, and the chemicals got up within the glass bundle, which are fairly coarse bundles, and that created a path for a filament of copper to grow through there. So again, there are several things that went wrong with this, and it really needed better materials, and sometimes it needs a better design too, where you could see where the whole wall over here is approaching. If you have the whole walls too close together, this is really easy to get. That's why we have standards, guidelines for how close your holes can be for different potentials. So, but you also need to go beyond good quality, not just that you've made it properly, but that the design does not inherently cause problems. Um, and you can't test in reliability. You would be using up its useful life if you were doing an actual test for reliability. It's a destructive test basically, right? Because in order to do a long-term test, you've used up its life in order to get those failures. So maybe there's some indicators that you can have that you can detect early on, but mostly the design needs to be vetted out early in the process. And so you need to do some modeling, you need to do testing. And the main thing is when you have a failure, you need to understand the failure mode and mechanism. It's not just statistics, but you need to understand what is going on so that you can make the change that will bring about a reliable product. And this is called reliability science or physics of failure. So, in that reliability science approach, it means you need to understand what failed and where and when it failed, what was the conditions that caused it to fail, how did it fail, what the mechanism is, so that you can address that. And then what was it, basically, why did it fail? And go to, some people say go 5 whys, so that once you've asked why 5 times, you get to really the root of what the problem is. So, and I've just shown some failure analysis things here. Cross sections are always lovely. So you can see like a cracked capacitor that was likely because of overstress. Sometimes it was designed too close for the hardware that you're torquing, or at a fold point in the board when it's under stress. This is an example of too thick of gold. It's 8% gold, and you can see that there are big plates of gold tin in a metallic that make it so that this joint is brittle. This is an example of a failure during double reflow. So the part was soldered on the first time, and then it was flipped over, and it was separated from, during the second reflow, it separates from the intermetallic compounds, and it will never join again. It will connect for only a little while, and then it will come loose. And here's an example of FTIR where we were looking at some contamination to try to understand what it was, so then we could understand where it came from. Okay, so you need to figure all this out and correct it, redesign to avoid that, and then improve the test to find it earlier if you can, and track the effectiveness of your improvements. And then you will gain that reliability. Okay, so primary sources of poor reliability, voltage and current stresses. An obvious one is ESD. You want to have a design of your product that prevents ESD damage. For some of our products where they're very high frequency, you really can't have much in the way of the active part of the product. So that's very difficult to do. But what you can get with overstress is basically the part blows out. And this was an example where our customer had a device under test on an ungrounded cart, and the input, the charges that were developed from that cart, when they plugged it into our product, would blow it out. So we also need to do a lot of training of our customers on how to handle things properly because of that high frequency design and the precision for which we need to make our test equipment. Sometimes we can't put a lot in between your product and ours. So, but yeah, damaged components can fail open or short, and you're going to get problems from each of those. So, and then there's also the current stresses from voltage stresses from just ongoing overworking. So we always derate our components so that we're operating at a voltage less than what the maximum is. We have tools to evaluate that, and we try to design for robustness to ESD damage to the extent that we can, and then again, test it a lot. And another one is mechanical design. So this was of a computer or something. Anyway, I couldn't find a good one in our examples, but we do extensive shake and shock tests. We do a drop test to make sure that it doesn't fall off that if it falls off the DHL truck, it doesn't break. So we do a bunch of testing to make sure that it gets to our customer successfully, and that it we test it to the point where it breaks, and so we can see what's going on and continue to do that until really everything's breaking, so you can't really fix all of it because you've abused it so much. So in power and is also another important mechanical design, power distribution, making sure you don't have hot spots and that you're getting the power away to the extent that you need it. So tolerance analyses and analyzation with modeling and simulations. and test, 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 and then make sure you have enough of the prototypes to allow for physically destructive testing. Once you have a good design, then you don't have to continue testing. And we've seen that where with the good design, a lot of these things no longer need to be tested again, except for maybe the next version of the product. So thermal issues are another one. If parts get overheated, they wear out really quickly. You need to have good heat sinking and good airflow. And again, analyze with modeling and measuring of prototypes. You can have mechanical stress from differential coefficient of thermal expansion. And if you have a large temperature swing throughout its life, it pushes and pulls on a solder joint, and you get a fatigue failure like what is shown here. That it's basically from that pushing and pulling, that thermal cycling, it has torn it apart. So that's not good. And another one is contamination. So I have some process residues here. Again, that there's not much in design we can do about that other than make sure we don't have pockets that could hold that. This is a mistake where somebody has used a liquid flux for point-to-point soldering, which is never allowed, or maybe they just didn't clean the flux off. But it has got the milky look of an undeactivated or unactivated, depending on how you want to describe it. But it's basically an uncured flux, and if it's gooey, if it's milky, chances are it's going to be slightly conductive and it's going to cause problems. This is an example of a resistor in a sulfurous atmosphere. And the silver that's exposed right at the termination up there has combined with that silver to make these beautiful flowers and leaves of silver sulfide. And those will fail open. So again, for us, we expect our products to be in fairly clean atmospheres. We're actually developing a white paper within INEMI on describing what that means, and it should be released soon-ish. But we need to make sure that the atmosphere that our products are in are not going to cause issues with the product and cause them to fail. Okay, so if you've got a design and reliability, there's a few basics. And one of the first is, are you leveraging from something? And does that product have a high failure rate? This is an example of, this is basically a cumulative failure rate. And this product here is failing at a much faster rate than this one down here. So this one was a redesigned leverage of the one above. And you can see that the failure rate is slower. So this is cumulative failure rate for all of the products that we've shipped. And so you can see that it's at a lower slope. So the improvements that were made between those made a big difference. And then the foundation, though, is, again, following the design guidelines. Those often include reliability issues, and they guarantee quality. So, and then you need good parts and suppliers. You can't just go by price. You need to go by capability, technical capability, process controls, good parts from good suppliers. And you need to look at their roadmaps and their quality performance and make sure that it's following and going along with what you need. Okay, and then execution. You know, again, design guidelines, they include reliability. Those need to be updated as you find out more about issues that can cause reliability. And you can analyze for known failure types and eliminate that. And then once you've got it in design, you can run stress tests and understand those early failure modes and mechanisms, eliminate those. If there's any early ones, those need to be taken care of. And then I say test to destruction. Basically test to the point where a lot of things are failing, and that way you can understand the longer term fail modes that fairly early on you can understand some of those and eliminate them where possible and mitigate. And then any failures and the solutions to those failures that you find, incorporate those back into the design guidelines. And also, you don't have to have everything fail yourself, right? You can learn from the technical conferences that are available, like IPC or SMTAI. There's a bunch of them where you can learn what has happened with others and then incorporate those fixes, those solutions that they have found into your own design guidelines so that you can avoid them from the start. And then you keep going in a circle. Um, Continue to analyze and figure out what has gone wrong and what you can do better, and continue to fix that either on that product or on the next ones. Okay, and that was it. So I just had a brief presentation, and if there are questions,
Yes.
I look forward to those.
Okay, great, Julie. It was a great, quick presentation and how Keysight can help in the reliability of materials in electronics. I'll take a quick 40 seconds break and we'll come back to the questions. Good morning, good afternoon, good evening. If you have just joined, welcome to the show, Global Electronics Friday Talk Show with your host, Rajiv Kulkarni. Yes, every Friday we bring this show to bring you the wealth of knowledge from our esteemed guests from the industry, and they are industry experts and also have an extensive knowledge in their own field. So Julie Silk, who is a program manager for reliability of materials in electronics with the Keysight Technologies, she gave a fantastic presentation just before the break. And this is about the reliability of materials in electronics. So Julie, one question comes is, how critical is anodic migration, though it is rare?
Well, it causes complete failure of the entire product. So it's very important. And it can sometimes be intermittent where it could blow out, so it's kind of hard to find. It's easy enough to avoid with good quality products, good quality laminate, and good drilling techniques. And I do think there's an impact from even the quality of the glass that's in the laminate. So we tend to have what I've seen is more failures in a humid atmosphere, a humid location, but there's no need to have that happen. It
Okay.
should be, yeah, it should be designed out from the start, that risk.
Okay. So another question comes here to my WhatsApp is, what are the strategies for improving materials reliability?
The strategies for improving, well, it really kind of depends. So, for instance, for the laminate selection, we have a list of laminates that have been approved by us, and those are the only ones that our suppliers or our fabricators are allowed to use. And where we get that information to a large extent is from one of our consortia. HDP does studies of laminate and their quality, and we leverage that in making our selections. For alloys, we typically just follow the industry, although I think there are some really good new ones out there that contain a little bit of bismuth, which drops the temperature of reflow just a little bit, which will help with some of the heat problems that we might get through reflow. And but it's hard for us to drive that because
Mhm.
even though we're a large company, in the big scheme of things, we're low mix, high volume, and or no, the other way around, high mix, low
High mix,
volume,
low.
and
Mhm.
it's hard for us to drive fundamental changes like the kind of solder contract manufacturer wants to use. But I still think some of these higher reliability solders would be a really good thing to do. So, um, and and then again, we have some unusual things that we have like electromechanical kinds of products because for high frequency signals, you can't digitize that. You need to the switching, and so you need to have mechanical um, um, materials, and then those can wear. They can have a little gunk on there, and understanding those and those take a lot of work to understand when there's something that's going on. So, but working with our consortia is actually really helpful. We not only get our questions answered, but we learn from everybody else during these
Definitely.
projects. And so, like Callison area and INEMI and the going to the conferences like SMTA and the knowledge
Yeah.
bases that they have, all of those really add a lot to our knowledge so that we can avoid things.
Excellent, excellent. And then we have another question here. What is your assessment on machine-induced ESD that comes from assembly process?
Well, again, we're a little unusual in that some of our parts are sensitive, like really sensitive to ESD. And I
Yeah,
know we've had some issues with, I think it was flying probe because everything's moving, I guess. And
yeah.
so there were some transients that were causing some issues on the board. Um, and so, yeah, we need to have those. I haven't heard of much in other parts of the process that have caused ESD, but it's definitely something that must be controlled. Some of our parts are very sensitive to ESD damage, and the problem with it too is you don't find out until later often, right? It lowers the lifetime of the part, and so it can get through all the tests, and then later on it can fail in the field, and that's always devastating. It's and expensive and unhappy for everyone.
Excellent, excellent. And finally, another question is, what are the benefits of reliable materials?
Oh, the benefits of reliable materials. Well, um, for a product like ours where people keep them for 20 years, 30 years, 40 years, it's vital. You don't want that to break. I mean, other things could go wrong or software could go out of date or, there are a lot of things that you want to go wrong, but when you have a field failure, so for instance, versus finding a failure internally, the cost of that is 10x, 100x what it would be if you caught it earlier. So something that fails later on and at the customer is very expensive. It can cause escalations and unhappiness, and sometimes in the customer's process, they have you know they have deadlines to meet and that sort of thing. You can't they hate it when they have to shut down. And so it's the benefits of using good quality materials is huge, and the payback is definitely there.
Excellent. I think that's all we have for today, the questions. And you want to uh, give any message to our audience, and you want to tell them where they can reach out to you uh, as far as Keysight, if they want to reach out.
Yeah, certainly. If you want to contact me, I had I'm sure my email's in there somewhere. Contact me if you have questions. And there's certain things I've focused on over the years, like the gold in sack solder. Not much work was done with that originally, and now I've commissioned several different organizations to look into that and do some studies, and we had some really interesting findings. Um, So that's one specialty. I've been involved in a lot of solder alloy studies, and I'm not the expert. In fact, I don't have any formal training in metallurgy, but I have learned so much from everyone that I've worked with that I can understand a lot of it, and I always know who to go back to. So I like to tell people if I don't know, I know who knows. And so if you have any questions, just contact me.
Excellent, Julie. And again, I thank all the audience out there who could watch and support and by sending their questions to our guest, Ms. Julie Silk, who is a program manager with Keysight Technologies. And if you want to reach out to Keysight, www.keysight.com. And definitely you can reach out to Julie Silk, and she's a program manager for any reliability questions of materials in electronics. And thank you again. And I know that yours is a West Coast Pacific time, and I woke you up early this morning and to come on to our talk show and share your wealth of knowledge. Thank you again. And to all the audience, next week we'll meet again at the same time and with another guest with another topic. Thank you all, and God bless. Thank you.
Bye.
Bye. Bye.